I'm a terrible drawer, and I'm even worse on this computer. So I'll do my best. Okay, so this is the next Y graph. On the y-axis, you have force. And then on the x-axis, you have displacement. So that's supposed to be a D. So we have force versus displacement.
Sorry.
So if we were to graph this, I can't use a different color, so I guess I'll just use the same color, but let's just say, oh, yeah, this probably would work. So let's say we have this. So we have plotted this, and so let's say we're exerting a constant force over a certain distance. So this would be the line on the graph that we have. So if we were to think about the area under here and find out what this would be. If I would do anything or not. So if we were to take that line and find this area below the line, think about how we'd find that. This is a square. So to get an area of a square, you just do height times length. So the height would be equal to the force. So if this were, say, 5 newtons of force, you would multiply that times displacement. So let's say it's 5 and 5. So you would, let me write that out really fast. So let's say we have 5 newtons of force for the Y reading, and you multiply it by the displacement, which we'll say is also 5 meters. We would get 25 Newton meters. So the units would just multiply together. You just multiply newtons times meters, which would be the same thing as a joule. So you have 25 Newton meters, which is equal to 25 joules. So what that is telling you is that when you multiply force times distance, you would get Newton meters or joules. You get work or energy. And we know that from the last chapter section, force times distance or displacement equals the work done. So that just is another way to think about it. The area under the curve of a force versus displacement graph always gives you work. So we looked at the equation before. This is just a different way to think of it graphically versus an equation. So I encourage you, if you haven't already, to get a notebook and write down, treat this like class. I think it's the best way to learn. I'm not going to grade your notebook because I can't, but it would help you to study for the test, especially this chapter, because there's things in the book that I won't go over. You don't have to know in the test. And so it would help you to just know what's important and what you can skip to study for the test. Okay, so that is the end of chapter 10. I want to move on to chapter 11 today. So I think I told you all yesterday, but I'm going to have 10.1 and then chapter 11 and one test. And we're going to skip 10.2. In chapter 11 too, we're going to skip some things on, but I'll just tell you what's important, what you can skip. But let's go ahead and start with chapter 11 today. Actually, sorry, that is not the title. That should go below here. The title is Energy and its Conservation. Okay, so this ties into the last chapter. We're talking more about energy, different forms of energy. So energy can come in many different varieties. So So certain kinds of energy would be things like light, heat, sound, magnetism, electricity, and they can be converted in between each other as well. So energy can be transformed or transferred into different forms. So for example, when you eat food, you take that energy and the chemicals and you break it down. By breaking down the energy and the chemicals, it turns it into heat energy for your body, electricity that runs your brain and your nerves, and motion that moves your muscles. So that would be one example of how you can convert energy that's found in the food, which is just stationary. You break apart the molecules, you then get energy that you can use to move, heat your body, and so on. Sorry, I don't know what happened right there. Get out of the way. Can you all read this okay?
Yes.
So I think last chapter we talked about the work energy theorem. Let me go ahead, actually. Not sure what I did there. Let's go and just clear all this out and we'll start over again. Okay, the work energy theorem. Did you all have all those written down? Is there anything you needed that I erased?
I think I missed the last note.
Okay, so energy can be transferred between forms.
Okay. I didn't get that.
The work energy theorem, the last chapter section, I think you should have in your notes, but just to review that. It was the one that looked like this. It was KE. Actually, I think it was like this. W equals delta KE. So that's the equation form of this. But what it says is that when work is done in the system, energy increases in the system. So there's two ways to state the work energy theorem. One way is this equation right here, which says that work equals the change in kinetic energy. Another way to state it is in words. When work is done on a system, energy increases in the system.
Miss Holly?
Yes.
So does that mean energy in a different system is decreased?
Yeah, very good. Exactly right. Yeah, that's a good point. So if you have a box, for example, right here, and you're pushing the box, so you are applying energy into the box. And whatever energy you give into the box, you've lost from your body and from the surroundings. So, and it's always the same amount. So if you were to expend 500 joules of energy, go ahead actually and just undo that. So you would have given 500 joules of energy to the box. So energy is always conserved and transferred. It's just like money. You know, if you lost $50 of money, that $50 went somewhere else. You know, it didn't disappear. It went to somebody else. If you lost it, you gave it to the store, somebody stole it from you, or somebody took it from you, but that money went somewhere else. Energy is just like that. It doesn't lose its value, doesn't disappear. You can't destroy it. You can't create it. You can only transfer it. So energy is transferred between things, and whatever energy you give up is given completely to something else. Now, there are cases, and this would be true for any case you have friction, where some energy would go into the ground. So it's not exactly true that all of your energy will go into the box, because some would go into the ground, some would go into the air, and so on. But the majority of the energy would go into the box. And if you added up all the energy you lost, it would be everywhere that you gave the energy to. And so, and the corollary is true too. Energy can move out of a system if you do negative work on the system. Does everybody have this down? Okay, let me clear all this. Okay, so there's two situations to think about, and it's similar to what I just showed you before. Now, if you have, I don't know actually why that changed like that. Let's see. I want that. There you go. Sorry, I'm learning how to do all this for the first time, and go ahead and do that again. Okay, now it should work. Okay, so if you are moving the box forward, so if your force right here is to the right, and the box is moving to the right, so both the force and the velocity are in the same direction. So we'll call this the positive direction. To the right is positive. So if both your force and the velocity are in the same direction, this box will increase its speed. It will go faster. And that's positive work. So when force and motion are in the same direction, positive work is done. And that would result in increasing speed. Almost had it that time. Okay, so the reverse is true too, where if you were to have the box going this way, so its velocity would be to the negative, but you still applied a force to the right. So you applied positive force because we said right is positive, but it's negative velocity because the box is going to the left, then that would be negative work. You're slowing it down, you're working against its speed. And so that would be work that is negative. It results in a decreasing speed of the box. You are decreasing the box's energy in this situation. So positive work would result in an increase in the system's energy. The box is the system, and you are either increasing its energy by making it go faster, or you are decreasing its energy by slowing it down. In this case, when force and motion are in opposing directions, negative work is done, and the speed decreases. Energy is taken out of the system, which in this case is the box. And the converse is true for this one. In this case, you have increased the box's energy, you've increased the system's energy. So positive work always increases the system's energy, but it would decrease the surroundings energy. Now you are giving energy to the box, that's energy you've lost from your body that goes into the box, into the surroundings. So by increasing the system's energy, you decrease energy in your own body. So energy has to go somewhere. Either it goes in or out of a system. And if it goes out of a system, it's negative work. Does everybody have this down? Let me erase all that. There's many different forms of energy. You know, for example, if you were to have do the same thing again. So if you were to have a boulder on a hill, and the boulder isn't moving, but it could move, that's stored energy. This is stored gravitational energy. So gravity, it would be what supplies the force that makes the boulder roll down the hill. So it has the potential, and it's better really to say that it's stored potential gravitational energy. Because gravity can be used to accelerate things, as you know, but it can also be stored. In this case, the boulder is not moving, so it's stored energy. It has the potential to move, but at this point it's not. Other examples of stored energy would be food. And so the food that you eat contains calories. That's energy that your body can use. It breaks down the molecules, and by breaking apart the molecules, that's energy that's released that fuels your body. Gasoline, another energy source. So the car breaks apart the gasoline molecules to run. There's also kinetic energy, which is energy in motion. And you can go in between kinetic energy and stored energy. So you can roll a boulder up a hill, and by rolling it up the hill, you are moving it. And so you're giving it kinetic energy by rolling it up the hill. That kinetic energy is converted into potential energy as you go higher and higher. So with every step, with every movement, that kinetic energy that you use is going into stored energy. And up here, the boulder has a lot more potential energy than it has down here. And that was due to you converting kinetic energy into potential energy as you moved up the hill. Other examples would be, say a bow and an arrow. So when you pull the bow back, see if I can draw an arrow. So that's supposed to be a bow and arrow. So as you pull the string back on the bow, you are storing energy within the bow, and then it slingshots outward. You then use that stored energy to move the arrow forward. And so you convert between kinetic and potential. You pull the bow back, that's kinetic energy that you're transferring into stored energy. Then you release the bow. That energy that's potential is then changed to kinetic energy as the bow goes forward. Another example would be a spring. So if you compress a spring, let me redraw that. That looks really bad. So if a string is compressed, so right now, it's not all that compressed. But if you compress the spring, then you give it stored energy. So by moving the spring forward, you've compressed it. And that gives it energy that can be used to slingshot it back out. And vice versa. You could also pull the spring apart, and that would then make it move back together. So springs store energy based on these curls right here. And by moving it past equilibrium or inward, you can then give it energy that you can release. So those are some of many forms of stored energy that we see. Does everybody have that down before we go on? Okay, so looking at kinetic energy's formula, kinetic energy equals 1/2 mv squared. I'm actually surprised at how well I could do that. That doesn't look that great, but better than I thought it would. All right, so 1/2 mv squared. And so what does that say? That kinetic energy is related to two things, the mass of the object and its velocity. So what that means is that, you know, the same object, actually let's say this instead. We have one object that weighs 5 kilograms, going at 1 meter per second. Another one weighs 10 kilograms, going at the same speed. So we have two objects. One weighs 5 kilograms, one weighs 10 kilograms, going at the same speed. How do the energies differ? Well, the one that weighs 10 kilograms would be double the energy of the one that weighs 5, because we can see that kinetic energy is related directly to the mass of the object. So this one would have twice the kinetic energy of the first. What if instead you had one object that weighs 5 kilograms going at 1 meter per second? And another that weighs the same amount, going double the speed. So in this case, we doubled the speed of the objects. So you might think that kinetic energy would also double, but it doesn't. Does anybody know what actually would happen in this case? How would this one compare to this one as far as energies go if you double the speed of the objects?
It would quadruple.
Very good, exactly. So, you know, if you were to
Nice, Anthony.
put a 2 in here, we know that 2 squared gives you 4.
There you go, bud.
So be aware of that. You know, it's going to probably be in the test where they'll ask you questions like that. And it's tricky because, you know, you might just assume it doubles as well. But, you know, if you have a square, it's not going to double, it's going to quadruple. So yeah, so this one would be 4 times the kinetic energy of the other object. So that's how mass and velocity will affect the energy of the object. This explains why things that move faster and things that weigh more hurt when they hit you. Because when something hits you, so if you throw a beanbag at somebody, that beanbag hits your hand absorbs that energy and it makes it stop. And so you've done negative work on the beanbag, which means you have transferred the energy from the beanbag into your hand. And that transfer of energy then goes into your cells, into your bones, into your muscles, and that can damage your cells. Energy can be damaging to your body if there's too much. That's why ovens burn, because an oven has heat energy, which can damage your cells, which causes burns. And so that's what we feel when things hit us. We're feeling the kinetic energy that we're absorbing and going into the body. Does everybody have that down?
Mm-hmm.
Just one last thing today. So if you were to throw a ball up in the air, so its displacement, that's supposed to be a D. Its displacement is positive, it's going upward. But what is gravity doing?
Pulling it down.
Exactly right.
Pulling it back down.
Good. So gravity is pulling it down. So we'd say that the force of gravity is negative.
Wouldn't it be at a down?
Sorry, you're kind of breaking up there. What'd you say?
So wouldn't it be at 9.8 meters per second squared downward?
Yeah, very good acceleration. Exactly.
Ooh, ooh.
Remember that. So yes, exactly. So we would say that the force of gravity is downward. So we'll say that's negative. In this case, the ball has a positive displacement. It's going upward, but gravity is acting downward on it. It's pulling it down. So we would say that that's negative work because the motion is opposed by the force. So gravity is doing negative work here. It's slowing the ball down. So there can be other things besides us doing work on things. And so there are forces that can do work on objects. Magnetism, electricity, gravity can do work on objects. So gravity is doing negative work in this situation because it's slowing the ball down. But of course, the reverse is also true if you have a ball falling down. So in that case, you have negative displacement, and then the force of gravity is also moving downward. So in that case, because both displacement and the force of gravity are in the same direction, that's now positive work and it's speeding up. Any questions about that before we go on? Okay, so I want you to do now, if you have your books with you, it's page 287. Just do 1 and 3. I assigned 1 through 7 on GradeLink odd, but we'll just do 1 and 3 today. I realize that we're gonna go pretty fast through this chapter. I don't wanna, I don't wanna rush anything. So let's just do 1 and 3 today, and we'll do the rest tomorrow. So just use this time if you want to work on those questions, and if you have any questions, let me know. I'll just give you about 20 minutes or so of time for you to work on the questions and ask me your other classmates for help, and then let's go from there.
Page 268.
Yes.